Hello and welcome to follow my videos. My name is Matti Ylitalo and today our focus is solar panel thermal simulation. Just a second, I'll put the presentation mode on. Solar panels are used to produce electricity directly from sunlight. A typical solar panel consists of a frame, glass panel and solar cells which are located in encapsulant to keep them in a fixed position, and then we have also some kind of a back sheet. Typically there are a number of solar cells connected together. I copied this example from a book. The book was this well-known Incropera's Principles of Heat and Mass Transfer. Here we see the detailed description of that problem. If you have this book, you can find out this analytical solution. But now our target is to solve this case using a Python code. Here we have the definition of our problem. We have a solar panel in which we have 3 mm glass layer, then we have 0.1 mm adhesive layer, and then this very thin silicon layer, and behind that is solder layer 0.1 mm and this aluminium substrate. And the solar irradiation is 700 watts per square meter, and we have air, and our heat transfer coefficient is 35 watts per square meter Kelvin. Now when we are calculating energy balance, we need to take into account what was mentioned in this problem definition. 7% of irradiation is reflected at glass surface, 10% was absorbed at top glass surface, and 83% is transmitted through this glass layer and absorbed in silicon. The reflective part does not participate in heating or power generation. Additionally, we need to take into account this electrical conversion inside silicon. The silicon converts part of the absorbed solar energy into electricity, and this efficiency is temperature dependent. And the remaining part will increase the temperature of our silicon layer. So we now have this kind of coupling, and we have a nonlinear problem. Higher temperature lowers efficiency, and lower efficiency increases thermal generation. We can now simplify our problem by assuming that this bottom part is well insulated and all heat generated in a silicon layer must escape from the top surface. So then we can calculate this conduction resistance. It's the thickness of the layer divided by its conductivity, and we can calculate this resistance for glass layer and for adhesive layer. When we are calculating heat balance of this glass layer, we need to take into account this convection. We have convection coefficient 35 watts per square meter Kelvin. We have surface temperature, and we have temperature of environment. But we have also radiation from this surface, and that's dependent on surface temperature and environment temperature. So the heat balance is that this convection and radiations are cooling down this glass layer surface, and we have heat generated in a silicon layer and some heat absorbed in that glass layer. So this nonlinear equation needs to be solved now. I asked this Python code from ChatGPT and calculated this case. It seems that it now gives this glass surface temperature 32.5 degrees C and silicon layer temperature 33.5 degrees C. So this calculated silicon layer temperature is only slightly above this ambient temperature. Ambient temperature was 20 degrees C, and that's because we now have so high heat transfer coefficient. It was 35 watts per square meter Kelvin, and that value is typical for forced convection case. If we have a natural convection only, this coefficient is typically below 10 watts per square meter Kelvins, and that can affect a lot on a silicon layer temperature. We need to notice that we now have many simplifications in our calculation. We assume that our bottom part is perfectly insulated, so all heat leaves upwards, and we are calculating only one-dimensional heat transfer, so no cone effects included now. And we have a uniform silicon temperature. In real panels we have always some kind of temperature gradients. How you can make this simulation more realistic? I think the first thing is that you include bottom heat loss. Typically there is quite high heat loss through this aluminium substrate. If you can assume that you have the same conditions, air temperature and heat transfer coefficient at the rear side also, so you need to calculate the resistance in this solder layer and in this aluminium substrate. So you can calculate the whole heat loss from this panel. If you have a CFD tools available, you can run two-dimensional or even three-dimensional temperature field simulation. The typical result is that the center is hotter and corners are cooler. We have now assumed that 83% of incoming radiation is absorbed in silicon, but you can also move to spectral analysis. That will give a more realistic results for this case. You can also start using more accurate efficiency calculation. We now have this simplified efficiency function. Typically in industrial cases we use this function to calculate the efficiency. And if you know the wind speed, you can calculate this heat transfer coefficient. We have now been using fixed value 35 watts per square meter Kelvins. If the wind speed is very low, then you need to move to using natural convection function, and then this heat transfer coefficient is typically below 10 watts per square meter Kelvins. You can also move to transient analysis. Then you will get information how the panel temperature is changing as a function of time. For example, from net you can find information how this solar radiation is changing during daytime. There is one thing which I want to point out. It is this panel efficiency calculation. If we have a solar load 700 watts per square meter and cell area 0.1 square meter, then this solar power is 70 watts. And we calculated this electrical output to be 14.3 watts. This means that the efficiency is 0.2, and we can say that panel efficiency is 20.4%. But if we calculate it so that we use this energy absorbed in silicon, that was 83% of incoming radiation. It means that the power absorbed in silicon is 58.1 watts, and our electrical output is 14.3 watts. So this efficiency is now 24.6%. So when you are talking about efficiency, be always careful and check how this efficiency is calculated. Okay, that was all this time. Thank you for watching and see you. Bye bye.